Hello and welcome to the Discrete Mathematics course in the Department of Computer Science at Tennessee State University. My name is Ali Sekman. I'm a professor of computer science at Tennessee State University. Let's get started. Okay, so this is Comp 3010 Discrete Mathematics. This week we are going to focus on the foundational topics of logic and proofs. And I'm going to talk about logic and proofs in a series of 5 lectures. Today we are going to talk about propositional logic and its applications, and then we are going to continue with propositional equivalencies, predicates and quantifiers. We're going to talk about rules of inference, and finally I'm going to introduce how to prove mathematical statements. So this is the first lecture in a series of 5 lectures. So let's talk about propositional logic. First of all, a proposition is a declarative statement that is either true or false, but not both. And the rules of logic give precise meaning to mathematical statements. So we are going to see how we can distinguish between valid and invalid mathematical arguments using propositional logic. And there are a lot of applications. And in fact, in the computer science curriculum, we are going to meet with many of them. For example, design of computer circuits. And when you take digital logic design course, you're going to see that the fundamental piece of circuits is transistor, and transistors can come together and build gates. And gates are basic implementation of propositional logic, as you will see. And computer programs are heavily using propositional logic as well. So again, a proposition is a declarative sentence or statement that is either true or false, but not both. Okay, for example, if you check the sentence, Washington, D.C. is the capital of the United States, that's a declarative sentence, and that is true in this case. If you say Toronto is the capital of Canada, that's a declarative sentence, which happens to be false. If we say 1 + 1 is equal to 2, that's a declarative sentence, happens to be true. 2 + 2 is 3, that's a declarative sentence, which happens to be false. Okay. So if we look at this, here, what time is it? That's not a declarative sentence, okay? So that's not a proposition. Read this carefully. Again, that's not a declarative statement. So that is not a proposition. X + 1 is equal to 2. Well, that's a declarative sentence. However, we don't know it is truth or falsity because we don't know the value of X. So therefore, that's not a proposition. Again, X + Y is equal to Z. Similar to that, since we don't know X, Y, and Z values, we cannot conclude if it is true or false. So therefore, that's not a proposition. Okay. And here is another example. Let's talk about Boston is the capital of Massachusetts. That is a declarative statement, which happens to be true. Miami is the capital of Florida. Well, that's a declarative sentence, but Tallahassee is the capital of Florida, so that's false. 2 + 3 is equal to 5. That is a declarative sentence, which is true. 5 + 7 is equal to 10. That's a declarative sentence, which is false. X + 3 is equal to 11. Even though that's a declarative statement, we don't know if it is true or false. That depends on X, therefore that's not a proposition. Answer this question is not a declarative sentence. Therefore, that is not a proposition, okay? So we will use a couple of conventions when we deal with propositional statements. Letters are used to denote propositional variables, and conventional letters are typically lowercase letters like P, Q, R, S, and then the truth value of a proposition is denoted by capital T if it is a true proposition, and capital F if it is a false proposition, okay? So T is for true, F is for false. So this is where we start the real lecture when we talk about compound propositions, okay? We can construct propositions using other propositions which are connected to each other, using one of logical connectives, as we will discuss now. And connectives includes negation. It includes conjunction. This is and, basically. Disjunction, which is or. Implication, and biconditional. So those 5 connectives can be used with other propositions to create new propositions, which are called compound propositions. So that's what we're going to discuss. Negation is the easiest one. The negation of a proposition P is denoted by this. My convention in this class will be to use P bar. Okay, so that is the negation, but your book uses this notation. So we are going to use both interchangeably. Okay. And proposition P naught means it is not the case that P. That's the opposite of P. That's very, intuitive. And some places, and you will see tilde P dash P, P naught, and P. These are maybe some other ways that some other books or internet resources might be referring to P naught. The most commonly used ones are, again, P bar or P naught, just like this one. So don't be surprised if I use this notation throughout the semester. Okay, here's an example. The earth is round. What is the negation, or what is P naught? If P is the earth is not, obviously P naught will be it is not the case that earth is round, or simply the earth is not round. Okay, Michael's PC run Linux. The negation of this proposition will be it is not the case that Michael's PC runs Linux. That means Michael's PC does not run Linux. Okay. It is not the case that Michael's PC runs Linux or Michael's PC does not run Linux. They are equivalent. How about this one? Vandana's smartphone has at least 32 gigabytes of memory. Well, this means it is not the case. The negation of this will be it is not the case that Vandana's smartphone has at least 32 gigabytes of memory. In other words, Vandana's smartphone does not have at least 32 gigabytes of memory. In other words, Vandana's smartphone has less than 32 gigabytes of memory. Okay. Okay. Well, very fast. Let's talk about those. Linda is younger than Sanjay. If that's a proposition, the P naught or negation of P will be Linda is not younger than Sanjay. May makes more money than Isabella. The opposite or negation will be May does not make more money than Isabella. Moshe is taller than Monica. Moshe is not taller than Monica. Abby is richer than Ricardo. Abby is not richer than Ricardo. This is very easy. So we're going to introduce truth tables. And truth tables are going to be heavily used in this class and in other classes, in some of the other classes, as you will get them in the computer science curriculum. A truth table is a table that shows all possible truth values of propositions. So what does that mean? For example, if we are discussing P and P naught, so if this is P, that's our original proposition. P can be either true or false. There are no other possibilities for P. It's either true or false. In that case, P naught, if P is true, P naught obviously will be false. If P is false, P naught will be what? True. So this is the truth table for what? Negation operation or connective. So here it is. P is either true or false, and P naught will be, if P is true, P naught is false. If P is false, P naught is what? True. So another connective is conjunction or and, okay? So if we have two propositions, P and Q, the conjunction of P and Q is denoted by P and Q, okay? And P and Q, think about this way. I mean, if you want to make it, you can say R is equal to P and Q. This is an atomic statement. This is another atomic statement. This is connective. In this case, and this is the compound statement, okay? Or compound proposition. Okay, so we use two propositions, P and Q, and a connective to create a compound proposition. So my question right now is that when do you think R will be true? Since this is AND operation, in order for R to be true, both P and Q must be true at the same time. If P is true, Q is false. Or if Q is false, P is true. Or if both of them are false, obviously R will be false, okay? So for example, if I say, if it is Sunday, let's say that P is, it is Sunday, Q is, it is raining. So then R will be, it is Sunday, okay, and it is raining, okay? So for R to be true, it must be Sunday and it must be raining. Assume that today is Saturday, so this is false. And assume that it is raining, that's true. But R is what? False. Even though it is raining, since it is not Sunday, the compound statement will be what? False. In order for R to be true, both of the statements must be true. So here is the truth table. P, okay, the truth table should list all possibilities for P and Q. Both of them can be true. The first can be true, the second can be false. The first can be false, the second can be true, or both of them may be what? False. So if both of them are true, compound statement or compound proposition will be true. In all other cases, the compound proposition will be what? False. So for example, if P is I am at home and Q is it is raining, P and Q means I am at home and it is raining. That's the compound statement or proposition, okay? For example, it says find the conjunction of the propositions P and Q, where P is the proposition Rebecca's PC has more than 16 GB of free hard disk space, and Q is the proposition the processor in Rebecca's PC runs faster than 1 GHz. Well, when we say conjunction, that means and, right? It's asking P and Q. That means Rebecca's PC has more than 16 GB of free hard disk space, and her PC runs faster than 1 GHz. Disjunction or. Again, now we have two statements, P and Q. Or is this connective? We call it P or Q. When you have two statements, if at least one of them must be what? True for the compound proposition to be true. For example, if this is S is equal to P or Q, if P is true, Q is true, compound statement will be what? True, or compound proposition. But if both of them are false, compound statement proposition will be false. If only one of them is true, the other one is false. That's enough for the compound statement to be true, obviously. So this is the truth table. If both of them are true, that's true. If at least one of them is true, compound proposition is true. If both of them are false, compound proposition is false. Recall when we have and, what did we have? If both of them are true, it is true. In all other cases, what? It is false. Okay. If P is I am at home and Q is it is raining, P or Q will be I am at home or it is raining, obviously. Okay, let's take it let's take a look at this example. Translate the statement, students who have taken calculus or introductory computer science can take this class. Okay, so what do we have here? We have OR, right? So this might be P, okay? So P is what? Students, a student has taken calculus, and Q is here. P is actually a student who has taken calculus can take this class, and Q is a student who has taken introductory computer science can take this class. And when you combine them with OR, you can simply say a student who has taken, students who have taken calculus or introductory computer science can take this class. So now I want to talk about the distinction between inclusive OR and exclusive OR. So far, actually, we have discussed only inclusive OR. Let's see the distinction. You are taking Comp 3010, and we have a prerequisite for this class. Either it is Comp 2140, which is Computer Programming 1, or Math 1910, which is Calculus 1. So if you're in this class, I expect that you have at least one of those courses, either Comp 2140 or Math 1910. If you do not have any of them, you shouldn't be in this class, okay? So when I say inclusive OR, if you have taken Computer Programming 1, you can be in this class. If you have taken Calculus 1, you can be in this class. What about if you have taken both of them? Well, obviously you can be in this class, right? So that's inclusive OR. So for P or Q to be true, either one of them, one or both of P and Q must be true, okay? So that's inclusive. How about this example, exclusive OR? You go to a restaurant and the waiter comes and tells you that soup or salad comes with this entry. What does that mean? That means you will get either soup or salad. You will not get both, right? That is exclusive OR. And exclusive OR is shown with a plus sign in a circle. So PQ means the compound statement, if you have this, R is equal to P exclusive OR Q. If this is true, compound statement is true. You will get, if you get, but if one of them is true, compound statement is not, compound statement is not gonna be true. But if both of them are false, yes, if both of them are false, obviously that's gonna be false. So that is here the truth table. Let's see. What did I say? I'm sorry, I think I made a little mistake. So if, in order for the compound statement to be obviously what? Yes, only one of them must be true. You cannot get soup and salad together. If both of them are true, that's false. The compound statement is false. But if you can get only soup, no salad, no soup, salad, then compound statement will be what? Proposition will be true. But if both of them are false, obviously the OR will be what? False. And here is an example. It asks, express the statement, I will use all of my savings to travel to Europe or to buy an electric car. What am I saying here? I have money. With this money, I will either go and travel to Europe or buy an electric car. I cannot do both, right? In order for the compound proposition to be true, only one of them must be true. So therefore, that is P exclusive OR Q. Okay, let's see. For each of these sentences, determine whether it's an inclusive OR or an exclusive OR. Coffee or tea comes with dinner. Either you get coffee or tea, not both, right? So that's an exclusive OR. A password must have at least 3 digits or be at least 8 characters long. Well, if it has 3 digits, you are fine. If it has more than 8 or more characters, you're fine. What about if you have both? If you have 9 characters and that includes 4 digits, you're still fine, right? So that's inclusive OR. The prerequisite for the course is a course in number theory or a course in cryptography. So if you have a course in number theory, you're fine. If you have a course in cryptography, you're fine. What about if you have a course in number theory and of course in cryptography, you're still fine. So that's inclusive OR. You can pay using US dollars or euros. Well, you go to an exchange station or exchange office, and then, or you go to a coffee shop in an airport, and they say you can pay with US dollars or euros. Well, it depends how you look at it, but the way I look at it is you can use US dollars or euros or any combination, so that will be inclusive OR, okay? But you can also look from another perspective. I'm gonna just skip it. This is very important. So we have seen negation, we have seen AND, conjunction, and we have seen OR, which is disjunction, and now we are gonna see implication, conditional statement. This is pretty important, okay? Assume that we have two propositions, P and Q. P implies Q. This is, let's say, P implies Q. This is a proposition, this is a proposition, this is connective, and this is a compound proposition, okay? So what does it say? If P is true, then Q. That means P implies Q, okay? This is a little tricky, and here is the truth table. What does that mean, actually? Let me discuss with an example. Assume that P is it is Sunday. Q is I go to beach. Go to the beach. Okay. Okay. So P implies Q means if it is Sunday, then I go to the beach. Okay, so now my question to you. If it is Sunday, and if I go to beach, what does that mean? The compound statement is true. This is true, and this is true. That means the promise that I have, I say, if it is Sunday, if the condition is true, then I will perform something or I will do something. So if the condition is true, and if my conclusion is true, then the compound statement is true, okay? So true is going to be true. How about if it is Sunday, but I do not go to beach? That means it is true, but I didn't go to beach. That means I did break my promise, okay? So the compound statement or compound proposition will be false. Here is the trick. What if it is Saturday? What if it is Sunday? That means what if this is false? Well, if it is not Sunday, I did not promise to do anything. So that means I did not break any promise. So if P is not true, if P is false, no matter whether if I go to beach or not, I don't break any promise. So that means if the P is false, Q is true, or P is false, Q is false, doesn't matter. I did not break anything. So that means compound statement or compound proposition will be what? True. So here is the truth table for this. If both of them are true, then the compound proposition is true. If the first one is true, if it is Sunday and I don't go to beach, compound proposition is false. If it is not Sunday, that means P is false. No matter what Q is, whether I go to beach or not, I did not break any promise. So compound proposition will be what? True, okay? Well, by the way, P is called premise and Q is called conclusion, okay? Well, again, one way to view the logical condition is to think of an obligation or contract. Think about this. You're a politician and you give this promise. If I'm elected, then I will lower taxes. Well, good. Assume that you're elected and assume that you did lower the taxes. That means you kept your promise. Assume you're elected, but you did not lower the taxes. That means you did not keep your promise. Assume you are not elected. In that case, whether you lower taxes or not, you do not break any promise because the condition is not satisfied. That means compound statement is gonna be true. In this one, this is false, obviously, okay? So that's one way you can look at it. Another example, assume you're in this class, I'm teaching it, and I tell you that if you get 100% on the final, then you will get an A. And then you get 100% on the final, and I give you an A. That means I keep my promise. The compound proposition is true. Assume that you get an A, you get 100% on the final, but I refuse to give you F. That means I do not keep my promise. Assume that you did not get 100% on the final. Whether I give you A or not A, doesn't matter. I did not break any promise. So compound proposition is what? True. So it's easier to look like this way, maybe an obligation or a contract approach. Okay. Here's an example. Let's say determine whether each of those conditional statements are true or false. Let's recall this. Okay, let's put it here. If both of them are true, it is true. If the first one is true, second one is false, it's false. If the first one is false, no matter what the second one is, compound proposition is true. Here, this is P. Here, this is Q. So P is true. 1 plus 1 is 2. That's true. 2 plus 2 is 5 is false. So true, false. True, false is false. Okay. So this will be what? False. Okay. Then let's look at this. This is P, which is false. This is Q, which is true. False, true is what? True. So this will be what? True. And this is again P, which is false. This is Q, which is false. False implies false is true. So that means compound proposition will be what? True. And here, this is P, which is false. This is Q, which is false. False, false, compound proposition will be true. If monkeys can fly, then 1 plus 1 is equal to 3. Since monkeys cannot fly, I do not break any promise or any obligation. Whether 1 plus 1 is equal to 3 or not is irrelevant in this case. Okay. So what are the other different ways to express P implies Q? You can say if P, then Q. If P, comma Q, Q unless P not. Well, this is a very interesting way of looking at it. For example, if I say, if it is Sunday, then I go to beach. Okay, let's put it here. Sunday. If it is Sunday, then I go to the beach, right? So this is P, this is Q. If Sunday, then I go to beach, and I go to beach unless it is not Sunday. Yeah, and this is equivalent to this. You see that? I go to beach. Well, let's see. Let's see here. Yeah, that's very clear. Q if P, Q whenever P. These are different ways of expressing P implies Q. Q follows from P, or P implies Q. P only if Q, Q when P. This is important. P is sufficient for Q. In order for me to go to beach, it is sufficient that it is Sunday. Q is necessary for P. Okay. Q is necessary for P, or you can say a necessary condition for P is Q, a sufficient condition for Q is P. These are all equivalent ways of saying that P implies Q. Okay. This is important. Converse, contrapositive, and inverse. Assume that you have P and Q, and P implies Q. So the converse of P implies Q is Q implies P. Contrapositive of P implies Q is Q naught implies P naught. I will show any with examples. And the inverse of P implies Q is P naught implies Q naught. Always keep this in mind, okay? So for converse, so you have P implies Q. Converse is going to be Q implies P. Contrapositive will be Q naught implies P naught. Okay. And then inverse will be P naught implies Q naught. Always remember this. So here is an example. It says, it is raining is a sufficient condition for me not going to town. Okay. So here is P. P is it is raining. And Q is I do not go to town. So if it is raining, then I do not go to town. Okay. So it is raining is a sufficient condition for me not to go to town. So what is the converse? Converse is Q implies P. That means if I don't go to town, then it is raining. Okay. If I don't, what is the inverse of Q? What is the inverse of Q? If I go to town, then it is raining. Okay. What is the contrapositive? Q naught implies P naught. So Q naught will be I go to town. If I go to town, then it is not raining. Inverse is P naught implies Q naught. That means if it is not raining, then I go to town. Okay. So here you go. And this is simply, we are talking about converse. This is Q. This is P. Q implies P. Okay. And inverse, this is P naught. And then this is, this is P naught, and this is Q naught. And this is Q naught, and this is P naught. Okay. All right, so find the contrapositive, converse, and inverse of propositional statement. The home team wins whenever it is raining. Okay, whenever it is raining. So what is P? What is Q? This is P. This is Q. That means P implies Q. If it is raining, then the home team wins. Okay. So what is contrapositive? Well, let's go in order. Converse is what? Q implies P. Contrapositive is Q naught implies P naught. And inverse is what? P naught implies Q naught. So considering those, converse will be if the home team wins, then it is raining. And contrapositive will be Q naught, which is if the home team does not win, then it is not raining. And inverse is if it is not raining, then the home team does not win. Okay, so here you go. Okay, and are we clear with that? Let's see. And this is home team does not win. This is Q naught, and this is P naught. And Q naught implies P naught is contrapositive. If home team wins, this is Q, okay, and this is P. That is the converse. Q implies P, and if it is not raining, that means P naught. And then this is home team does not win, which is Q naught. P naught implies Q naught is the inverse. I hope this is clear. And let's see this. State the converse, contrapositive, and inverse. So I'm going to do the first one, and then I guess you can do the next two by yourself. If it snows today, which is P, I will ski tomorrow is Q. This is P implies Q, okay? So the converse will be what? For converse, it will be Q implies P. That means I will ski tomorrow if I ski tomorrow, then it snows today. That's what it is. Contrapositive is what? Q naught implies P naught. That means if I will not ski tomorrow, then it does not snow today. That's what it is. Inverse is what? Inverse is P inverse implies Q inverse. That means if I will not ski tomorrow, then it does not snow today. Okay, so I'm going to skip the next two, and I hope that you can do it by yourself as an example. And then the next connective is biconditional. Biconditional is if and only if P, if you have this, R is equal to P if and only if Q. So for R to be true, both P and Q must have the same truth values. This means P will imply Q and Q will imply P. Okay, so, or let me put this way. That means Q implies P. You see that? So therefore this arrow is two directional or bidirectional. Okay. So for R to be true, Q and P must have the same truth values. If both of them are true, R is true. If both of them are false, R is true. But if one is true, the other one is false, then R is false. Here is the truth table. And here, as I said, if both of them are true, this is true. If both of them are false, this is true. But if one is true, the other one is false, biconditional is what? False. Okay. Okay. If P is I am at home and Q is it is raining, P biconditional Q means I am at home if and only if it is raining. Okay. I am at home if and only if it is raining. If I am at home and if it is not raining, okay, compound proposition is false because I said I am home if and only if it rains. I am home, but it is not raining. So that breaks a promise. If I am not home and if it is raining, it also breaks a promise. But if I am at home and if it is raining, it does not break the promise. If I am not home and if it is not raining, it does not break any promise. So it is still what? True. Okay, you can say if and only if, or P is necessary and sufficient condition for Q, or vice versa. You can say Q is necessary and sufficient for P. If P, then Q, and conversely, if P, if Q. These are different ways of representing biconditional. So now I'm going to talk about how we can create truth tables. Okay, so we are going to talk about the truth tables, which are extremely important, and I like you to focus on this. So let's talk about what a truth table is. We have already seen the connectives, but think about this. If we have only one proposition P, what are the possibilities for this proposition? It can be true or false, right? So if you only have one proposition, that can be either true or false. If you have two, P and Q, if you have two propositions, you have four possibilities. They can be both true. One can be true, the other one can be false. The first one may be false, the other one may be true, or both of them can be false. How about if you have three, P, Q, and R? Three propositions, P, Q, R. In that case, there are 8 possibilities. I guess you get the pattern that I used here. I said 4T, 4F, 2T, 2F, 1T, 1F. So this is 2 to the 1. This is 2 to the 2, which are 4 possibilities. And this is 2 to the 3, which are 8 possibilities. If we have 4 propositions, obviously 2 to the 4, 16 possibilities. Okay? So let's keep this one in mind. And here is the example. Construct the truth table of the compound proposition. So I'm going to do it from scratch with you. Okay, let's use this color. I have P, I have Q. And both of them, we may have 4 possibilities. Okay, so first I'm going to find P or Q naught. But in order to do that, first I need to take care of what? Q naught. So I will say Q naught. This is my notation for Q naught. As you know, they are also, this one and this one are exactly the same thing. Okay. So what is Q naught? If Q is true, Q naught is false. If Q is false, this is true, and so on. So this will be false, true, false, true. Now, once I have Q naught, I already have P, right? I have P right there. I have Q naught right here. So I'm ready to have P or Q naught. In order to do that, this is my P right there. This is Q naught, and this is OR operation, right? This is OR. So if you recall, true or false is what? True. True or true is true. False or false is false. False or true is true. So now I get this one. The next thing that I have to take care is P and Q. Well, I already have P and Q, so I'm ready to do this. P and Q. So here is P, here is Q. True and true is true, and all the others are false, right? This is for and. That means false and true is, for example, false. Now, I did take care of this, and I did take care of this. So that means right now, I have a proposition right here. This is a compound proposition. I have another proposition right here. That's also a compound proposition. And now I need to connect them with conditional connective, right? So now I'm going to go and I'm going to use this color now. P or Q naught implies P or Q. So that is even a bigger compound statement right now, right there. So my question here, I already have this guy, which is right there. And I already have this guy, which is right here. So I'm going to connect this column and this column with this connective, which is conditional statement. So now you can tell me true implies true is true. True implies false is false. False implies false is true. And then true implies false is what? False. So that is the truth table for what? For this compound proposition. What does that mean? This P and Q are atomic propositions. So that means if P is true, Q is true, all of this compound statement or compound proposition will be true. If, let's say, P is false, Q is true, the compound proposition right here will be what? True. So that's what it means. And here you go. So that's how you do it. Here is another example. Well, this is very, very simple. We have P and P naught. So P, okay, P naught, and then we will have P and P naught. P can be true or false, and P naught will be opposite of it. So now you can tell me what is true and false. This is P and P naught. True and false is what? False. What is false and true? That's also false. As you see here, this compound statement is always what? False. It is independent of P. Whatever P is doesn't matter. That's always false. That's, by the way, called contradiction, as we will see later. Here you go. So this is P, this is P naught. And then let's go to P or P naught. Again, if this is P, this is P naught, P or P naught, like that. This is true, false. This is false, true. True or false is true. False or true is true. As you see, this compound statement is always what? True, irrespective of the value of what? P. This is called tautology, by the way, as we will see later. Okay, so here it is. Here is another example. I want to do this from scratch as well. Okay, so now we have two P and Q. I'm going to start with P, Q. Always first write all possibilities. Okay, then I need to take care of now this compound statement right there has two pieces. One is this statement, the other one is this statement. Now I need to take care of this statement here. In order to do that, I need to take care of what? Q naught. So therefore, that's what I'm going to do. I'm going to go and add Q naught here. And that's very easy. False, true, false, true. As you see, that's the opposite of this Q right there. Now I have Q naught right there. I have P right here. So I'm ready to do what? P or Q naught. Here is P and here is Q naught. And the connective is what? Right here, or. So now you can tell me, for example, true or false is what? True. True or true is true. False or false is false. And false or true is what? True. Now I did take care of this. In other words, right now I have this. I already have Q right here. Now I need to connect them with conditional statement. So I'm going to go and write here conditional connective, sorry. Q naught implies Q. Okay, so, and here is my Q naught right there. And then, sorry, here is my P or Q naught right here, and then Q is right here. So what implies will be from here to here. True, let's see, true implies true. Is that true? Yes. True implies true is true. True implies false is false. If this is false and if this is true, remember the promise. So if the promise is false, no matter what the other one is, doesn't matter, right? So this is true. And if the promise is true, the conclusion is false, that means the compound proposition is false. So what does this mean? This means that, for example, let's take a look at this row. What does that mean? It means if P is false, Q is true, this compound statement or compound proposition will be what? True. Okay, so this is how you handle this. Here is another example. I want to do this as well so that you can have a better feeling about what to do with those kind of problems. We have P, Q. Okay. So again, all possible combinations. Okay. Now I have two compound statements, one here, and then I have a bigger compound statement, right? So that's what I'm going to do. First, I'm going to take care of P or Q. P or Q is obviously true, 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 false, because we know P or Q will be false only if both of them are false. And then I will have P and Q. P and Q is obviously true, false, false, false. Now I have P or Q implies P and Q. So here I have this and that. So the premise is true, conclusion is true. So that means compound statement is true. Premise is true, conclusion is false. That means compound statement is false. Premise is true, conclusion is false, false. Premise is false, conclusion is false, that's true. So what does that mean? For example, this row right there, it means if P is true, Q is false, then this compound statement right here will be what? False. Okay. All right, let's do this too. I mean, why not? This is pretty easy. So we have P, Q. I'm doing this on purpose so that you can have a better feeling about what to do in those kind of problems. Again, true, true, false, false, true, false, true, false. Now let's look at this. I have one compound statement here. I have another compound statement here, and then I have a bigger compound statement, okay? But in order to take care of this compound statement, I only need P and Q, and I have them. But in order to take care of this compound statement, I need Q naught and P naught, right? So that's what I'm going to do now. I'm going to say Q naught and P naught. Q naught is the opposite of this column right there, which is false, true, false, true. Okay. And then P naught is the opposite of this P right there. So it's going to be false, false, true, true. Now, see, I have Q naught, P naught. Now I can say, first let's take care of this. P implies Q. Okay, here is P, here is Q. And this is the premise, and this is the conclusion. Premise is true, conclusion is true. That means this is true. Premise is true, conclusion is false. It is false. Premise is false, conclusion is true. If the premise is false, no matter what the conclusion is, we always have true as the compound proposition, right? Then I'm going to take care of Q naught implies P naught, which is right here, okay? Q naught implies P naught. F, if premise is F, conclusion is F. If premise is false, regardless of conclusion, I did keep my promise. Premise is true, conclusion is false, this is false. Premise is false, conclusion is true, this is true. Premise is true, conclusion is true, that's true, obviously. Now, I have this guy right there and this guy right there, and this time the connective will be what? Biconditional. So I'm going to go and write it here. P implies Q, biconditional, and then Q naught implies P naught. Let's remember biconditional. Biconditional means if the premise and conclusions are the same, if both of them are true or both of them are false, then the compound proposition is true, right? So now I'm going to go here. Premise is true, conclusion is true. This is bidirectional, so that's going to be true. If premise is false, conclusion is false, since it is bidirectional, this is true. True, true is true. True, true is true. So that's actually a tautology right there. What does that mean? That means for any P or Q, doesn't matter. You always get what? True for this. Right there. That's a tautology. Okay, so here is another example, but I'm not going to do it from scratch. Let's go over it. We have PQ, true, true, false, false, true, false, true, false. We have 4 possibilities. P implies Q. Premise is true, conclusion is true, compound statement is true. Premise is true, conclusion is false, it is false. Premise is false, no matter what the conclusions are, we always what? True. Now Q implies P. We'll go from here to here this time. So from here to here, we are going to connect them, right? Okay, so now Q, premise is true, conclusion is true, that is true. Premise is false, conclusion is true. If the premise is false, regardless of the conclusion, the compound statement is true. Premise is true, conclusion is false, it is false. Premise is false, whether the conclusion is false or true doesn't matter. The compound statement is what? True. Now, I have this guy right here. I have this guy right here. Now I'm going to connect them with this connective, which is conditional, right? So now premise is true, conclusion is true, so compound statement is true. Premise is false, conclusion is true, compound statement is true. If premise is true, conclusion is false, it is false. If premise and conclusion are true, that is true. Okay, so let's do only one of them together, and then I'm going to ask you to do it by yourself. I'm going to do one of them in detail and then give the answer for the others, but I like you to work on them by yourself. So let's go ahead and let's do the first one, A. So this is P, this is Q. Okay, this is true, true, false, false, true, false, true, false, all possible combinations, right? So now I have already have P, I need Q naught. So I will just do Q naught right there. Q naught is opposite of Q, false, true, false, true, okay? All right, now I can do P implies Q naught. Here is P, this is the premise, this is the conclusion. Premise is true, conclusion is false. So that is false. Premise is true, conclusion is true, that is true. False, if the premise is false, no matter what the conclusion is, it's always what? True. So that's the first one. And you can obviously do the rest. So I'm going to give you here the answers, and then I'd like you to work on them by yourself. Again, this is similar, and I'm going to do only one of them, and let's do the first one, and then you work on the others. But this time, please note that I have 3 propositions. If I have 3, that means I have 8 possibilities, right? So I'm going to put P, Q, R, okay? And in order to construct, I'm going to put 4 true, 4 T, 4 false, 4 P, and then 2 T, 2 F. And then F through F, F through F. Okay, now what do I need? I already have P, and I need to take care of this compound statement here, and then the larger compound statement. And what I need Q naught. So I'm just gonna go and put Q naught right there, okay? So Q naught is the opposite of this Q. That's very easy. I will say false, false, true, true, false, false, true. Sorry. Okay. True. Okay. And then I need to do what? I need to do Q naught or V. Q naught or R, sorry. Q naught or R. Well, you guys can tell me this is Q naught right here and R is here. I'm going to connect them with OR. Well, you tell me false or true is true. False or false is false. True or true is true. True or false is true. False or true is true. False or false is false. True or true is true. True and false is what? True. Sorry. Okay. Now I can do this. P implies Q naught or R. As you see here, P, we already have it here. Q naught or R, we already have it here. That means this column and this column. So this is premise, this is conclusion. True implies true. I'm not going to do it, very long. true, true is true, true, false is false, true, true is true, true, true is true, false, true is true, false, false is false, no, true, sorry. If the premise is false, the conclusion is false, conditional connective is true, false, true is true, false, true is true. So that's what it is. So I like you to do the rest by yourself, but I'm going to give you the answers for them, okay? What does equivalent proposition? This is very important. True propositions are equivalent if they always have the same truth value. Okay, so what does that mean? If you construct truth table for two propositions, for example, here, I have one proposition right there, and I have another one compound proposition right here, another compound proposition right there. So the truth table shows that these are the truth values for what? P implies Q, and these are the truth values for Q naught implies P naught. They are exactly the same. For the same input, they generate the same output. That means P implies Q is equivalent to Q naught implies P naught. Okay? So those two propositions, the first proposition, compound proposition, and second compound proposition are equivalent because they generate what? The same truth table. Recall contrapositive. What was contrapositive? If we have P implies Q, contrapositive was Q naught implies P naught, right? So as you see, the compound statement and it is contrapositive, the conditional proposition and its contrapositive are equivalent, basically. Okay, another concept, precedence of logical operators. This is just like mathematics. For example, when you have multiplication comes before addition, right? So similar to that, negation comes before and or operators. And or comes before conditional or biconditional operators. For example, if we are given this one, what does that mean? Well, we have or, conditional, and then negation. We have three connectives. The first connective is here, second is here, third is here. Which one has the higher precedence? This one has higher precedence, right? So basically this is equivalent to, and then or, and then this. So this is equivalent to saying P or Q implies R not. First, get the inverse of R, and then do P or Q, and then do conditional connective. So that's the order. So if you want to do it this way, you have to use parentheses, okay? Because otherwise, without parentheses, this guy means this. Well, sometimes instead of T and F, we can use 1 and 0, okay? And 1 represent true, 0 represent false. That's because 1-bit representation. So when you have truth tables, for example, we had this P, Q, right? We had true, true, false, false, true, false, true, false. Let's say P and Q was true, false, 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 right? We can write this one as P, Q, P and Q, like 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, right? But the common convention is if you are dealing with ones and zeros, you always start with, you typically start with zeros, like 0, 0, 1, 1, 0, 1, 0, 1. Instead of true, true, false, false, you do false, false, true, true. Doesn't matter. So 0 or 0, that means false or, sorry, 0 and 0 is 0, 0 and 1 is 0, because this is false and false, false and true, true and false, and true and true. So that's another way. Instead of T and F, you can use 1 and zeros, okay? Here is an example. Well, here you go. We have X and Y, 0, 0, all possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. There are no other possibilities. and this is or false is false, false or true is true, false, true or false is true, true, and true or false is true, and so on. So you can use zeros and ones. Okay. All right, so here are some very, very simple examples. What is the negation of each one of those propositions? May has an MP3 player. Negation will be May does not have an MP3 player. There is no pollution in New Jersey. And the negation will be there is pollution in New Jersey. 2 plus 1 is equal to 3. Negation will be what? 2 plus 3, 2 plus 1 is not equal to 3. The summer in Maine is hot and sunny. This is a little tricky, okay? First, these are all easy. Now, the summer in Maine is not hot, okay? And here, this and becomes or, and sunny becomes it is not sunny. So I will talk about this a little bit later when we take the inverse. Here, let me tell you very quickly, this is P and Q, and we want to get, see, P is the summer in Maine is hot, Q is the summer in Maine is sunny, and I want to negate it. And we will see a little bit later that this is equivalent to P naught or Q naught, the Morgan's law, but we will talk about it later. So the negation of this will be the summer in Maine is not hot, or the summer in Maine is not sunny, okay? Okay, here you go. What does it say? P is the swimming at the New Jersey shore is allowed, and Q is sharks have been spotted near the shore. So what is Q naught? If Q is sharks have been spotted near the shore, Q naught will be what? Sharks have not been spotted near the shore. And P or Q, swimming at New Jersey shore is allowed, and sharks have been spotted near the shore. P naught or Q, swimming at New Jersey shore is not allowed, or sharks have been spotted near the shore. P naught implies P implies Q. If swimming at New Jersey shore is allowed, then sharks have not been spotted near the shore. That's what it is. How about this one? If sharks have not been spotted near the shore, then swimming at New Jersey shore is allowed. How about this one, P naught? If swimming at New Jersey shore is not allowed, then sharks have not been spotted near the shore. Okay. How about this? Swimming at New Jersey shore is allowed if and only if sharks have not been spotted near the shore. That's what it means. How about this one? This may be a little bit tricky. So this means swimming at the New Jersey shore is not allowed. And this means swimming in New Jersey shore is allowed, or sharks have not been spotted near the shore. Okay. So this statement will be here, swimming at the New Jersey shore is not allowed, and either swimming at the New Jersey shore is allowed, or sharks have not been spotted near the shore. Okay, very simple. Okay, so now another example. This time we have P is it is below freezing, Q is it is snowing. Okay, it is below freezing and snowing. So this means what? You can tell me P and Q. It is below freezing and snowing. It is below freezing but not snowing. It is below freezing but not snowing, right? So let me put it here. So here, let's say it is below freezing and snowing. We have and. It is below freezing and not snowing. It is not below freezing. It is not, and it is not snowing. Okay, and it is either snowing or below freezing or both. That means inclusive or P or Q. If it is below freezing, it is snowing. That is conditional. P implies Q. Here, either it is below freezing or it is snowing right here. Okay. Either, that means right here, this is what it is. And it is not snowing if it is below freezing. That means if it is below freezing, P implies Q naught. Because if it is below freezing, then it is not snowing. If it is below freezing P, then it is not snowing. P implies Q naught. That it is below freezing is necessary and sufficient for it to be snowing. That means P if and only if Q, or Q if and only if P. Well, there are a lot of applications of propositional logic, and we're going to see a couple of them. One is translating sentences to propositional logic. We can translate from English to or mathematics. And system specification is a very important area of software engineering. When you develop a software system, there are different phases. For example, you start with requirements analysis, which leads to development of system specifications. Then you design, implement, test, and so on. So propositional logic is extremely useful in system specifications or writing down system specifications mathematically. And logic puzzles, logic circuits are some applications. Let's see a little bit each one of them. For example, if you have this English statement, if I go to Harry's or to the country, I will not go to shopping. Well, you can identify atomic propositions and represent using propositional variables. So I have 1, 2, 3 atomic propositions. P is I go to Harry's, Q is I go to country, R is I will go shopping. And then find the appropriate logical connectives. What does it say? If, right? If P or Q, then R. Okay. P or Q implies, sorry, R not, because it says I will not go to shopping. So that's R not. So this statement in English can be represented with this propositional compound proposition using P, Q, and R atomic propositions with or, negate, and or inverse and conditional connectives. Okay, so this might be a little bit tricky. You cannot ride the roller coaster if you are under 4 feet tall unless you are older than 16 years old. So in order to ride the roller coaster, there are 2 conditions. One, you must be older than what? 16 years old. Another one, you should be taller than 4 feet. Otherwise, you cannot ride the roller coaster. So let's say that Q is atomic proposition. You can ride the roller coaster, okay? And assume that this is R. You are under 4 feet tall. That's another proposition. And this is another one, which is S. You are older than 16 years old. What does this say? You are under 4 feet tall and you are not older than 16 years implies you cannot ride the roller coaster. Okay, that's beautiful, right? So R and S naught implies Q naught. So the whole sentence right here can be represented mathematically with this propositional logic like that. Okay, here's another example. What does it say? You can access the internet from campus only if you are a computer science major or you are not a freshman. Okay, if you are a computer science major, whether you are a freshman or not, you can access to the internet. But okay, but if you are not a computer science major, you have to be not a freshman. Okay, so let's see. Okay, so assume that this is the proposition A. You can access the internet from campus. Okay, assume that this is proposition C. You are a computer science major. Okay, and this is proposition F. That means you are a freshman. You are a freshman is F, not okay. So what does that mean then? This is very easy. You can access to the internet from campus. implies that you are either computer science major or you are not a freshman. Okay. Okay, software specifications. As I said, it's very important in software engineering, in systems engineering, that software specifications or system specifications are developed prior to design, mostly. Any mistake that you do in system specification may lead incorrect design, incorrect implementation, and incorrect product. So it's extremely important that specifications are consistent, complete, and fully understandable for the developers and also for the customers. So you can express using propositional logic the specifications so that they are not debatable. For example, here, the automated reply cannot be sent when this file system is full. Well, it's very easy. I mean, maybe you can say P represent the automated reply can be sent as a proposition. Q is the file system is full. What does this say? Q implies P not. That means if file system is full, then you cannot send an automated response. That's easy condition, right? If the file system is full, then you cannot send an automated response. Okay, this is fun part of discrete math. Let's see if we will be able to solve this puzzle. Assume we have an island, and in this island we have two kinds of residents. Knights always tell the truth, or knaves who always lies. If there are like 100 people in the island, either they always tell the truth. I mean, each person in the island always tell the truth or always tell lie. Okay, you cannot have a person who sometimes tell the truth, sometimes tell the lie. Okay, either they tell the truth or they lie. So now you go and meet two people, and people A says, okay, you meet with two people, right? This is the first person, this is person A, and this is person B. Person A says B is a knight. Okay, you talk to person A, and person A says, the person you see that B is a knight. And B says, two of us are of opposite types. B says, if I am a knight, A is a knave. If I am a knave, A is a knight. So the question is, what is A, what is B? Is A a knight or knave? How about B? Is it a knight or knave? How do you solve this puzzle? Okay, actually that's pretty simple. Assume that we have, okay, let me do it this way. Assume that we have, I don't want to do it this way. Okay, so assume that we have two propositions. P is A is a knight, and Q is what? B is a knight. Okay, so I have two propositions, P and Q. P is A is a knight, and Q is B is a knight. Okay, let's assume P is true. Let's assume that proposition P is true. What does that mean? That means A is a knight. If A is a knight, A always tells the truth. So that means B must be a knight as well, right? That means if P is true, then Q must be true. Is that right? Because we assume that P is true, that means A is a knight. Since A always tells the truth, and if A is saying B is a knight, B must be a knight. That means Q must be true. But B says two of us are opposite types, right? Since B is a knight, what it says must be true as well. What does he say? He says P, okay, and Q naught or P naught and Q must be true. So that means if P is a knight, Q must be a knave, or if P is a knave, Q must be knight. So this must be true. But now let's look at this. P is true, Q is true. So this is true and false, or false and true. What is true and false? That is false. Or false and true is false. That is false. Well, that means this statement is false. But if B is a knight, that statement was supposed to be true, right? So that means B is not a knight, okay? So Q is false, okay? So that means P implies Q. This is true, this is false, this must be false. So what P says must be false. That means P cannot be a knight. So the conclusion is both A and B are knaves. So I suggest that you look at this puzzle by yourself and understand. Logic circuits, well, logic circuits are extremely important. And when you take a computer organization, operating systems, and digital logic design, some other courses, you're going to learn that logic circuits are the lowest level. It's not the lowest level, but you know, the computers, right? Computers have circuitry in them, okay? And the most, I mean, the very, very basic circuitry that we use are transistors. And transistors come together and then they can create logic gates like an inverter. An inverter is nothing but negation. An OR gate. OR gate is nothing but what? Disjunction or just the OR operation. An AND gate is nothing but what? An AND AND connective, right? So, and you can generate more complicated circuits using combination of inverters and OR gates and so on. Later in the curriculum, you're going to learn about them anyways. Okay, so this concludes the fundamentals of propositional logic. As I said, this is the first lecture of a series of lectures that I'm going to have, and hope to see you in the next lecture.